Hello there and welcome to the GameWise. I'm so excited that you're here. The daily life becomes so hectic, all the work and stuff of the world make us so tense and stressful that we sometimes forget what we even are. This video is your gateway to some moments of quiet and calm solitude. Whether you're going to sleep or just trying to relax a bit, this video is perfect for you to relax while we gently discuss the most violent phenomenon of the universe, an explosion billion times brighter than the sun itself. The supernova, its birth and what it exactly is, our ancestors who witnessed it, and much more. I would also like you to mention from what part of the world you are watching and what is time there. And yes, subscribing is always appreciated. Let's begin. Space is quiet, almost too quiet. Out there, stars are born, galaxies swirl, and time stretches out beyond anything we can really grasp. But once in a while, something incredible happens. A star explodes. And not just any explosion. This one is so powerful, it can outshine an entire galaxy. That's a supernova. It's hard to imagine something that massive just ending. But it's not really an end, not in the way we think about it. A supernova is what happens when a star, after spending millions or even billions of years burning bright, finally runs out of fuel and loses the fight to gravity. And instead of quietly fading away, it goes out with the biggest bang in the universe. Let's take a step back. A star isn't just a ball of light hanging in the sky. At its core, it's a nuclear engine. It's been holding itself together for eons, thanks to a balance, a kind of tug of war between two forces. Gravity is constantly trying to pull it inward, to collapse it, but deep inside, fusion reactions are pushing outward, releasing heat and light. That balance is what keeps a star alive. But it doesn't last forever. The star keeps fusing elements, starting with hydrogen, then helium, and eventually heavier stuff like carbon and oxygen. This process releases energy until it hits iron. Iron is the dead end. Fusing iron doesn't release energy, it eats it. And once the core of a star fills up with iron, everything starts to fall apart, literally. Gravity takes over. The core collapses in less than a second. The outer layers come crashing down too, and then, boom. All that energy gets released in one massive explosion. The star rips itself apart. That's the supernova. For a brief moment, that one dying star shines brighter than all the other stars in its galaxy combined. Think about that. One star brighter than hundreds of billions of others. It's wild. And the shockwave from that explosion throws the star's guts into space, everything it's spent its life making. And here's the crazy part. We need that. We need that explosion. Without supernovae, there wouldn't be gold or uranium or iodine. No iron for blood, no calcium for bones. The oxygen we breathe, the carbon that makes up everything alive, all of it came from stars that blew up billions of years ago. In a very real way, we are made of stardust. It's not just a poetic idea, it's science. Every atom in your body that's heavier than hydrogen was born inside a star and probably finished in a supernova. That's what makes these explosions so much more than just violent. They're part of a bigger story, a cosmic cycle, life, death, and rebirth written in fire and light. But as incredible as they are, not all supernovae are exactly the same. Some happen to massive stars, others to small stars that steal matter from a companion. There are different kinds, with different triggers, different signs, different fates, and if we want to really understand them, what they are, why they matter, we've got to dive deeper. Let's keep going. Not all supernovae are created equal. They don't all come from giant stars collapsing. In fact, there are a couple of different ways a star can go out with a bang, and each has its own story. Let's start with the most famous type, the core collapse supernova. This is the one we talked about already, where a massive star burns through its fuel, builds up iron in its core, and then suddenly collapses under its own weight. These are the dramatic ones. They happen in stars at least 8 times the mass of our sun. When these stars die, they die hard. What's left behind is often a neutron star, or if the star is big enough, even a black hole, a place where gravity is so intense, not even light can escape. But there's another kind of supernova that happens in a much sneakier way. It starts with a smaller star, specifically a white dwarf. That's the leftover core of a star like our sun, after it sheds its outer layers and quietly burns out. A white dwarf on its own is harmless. It just cools down slowly over billions of years. But if it has a companion star orbiting nearby, things can get interesting. Sometimes the white dwarf starts stealing matter from its neighbor. Slowly, it pulls in gas, growing heavier over time. And if it gathers too much, it crosses a critical limit called the Chandrasekhar limit, around 1.4 times the mass of the sun. When that happens, the pressure and temperature shoot up so fast that carbon fusion ignites all at once. The whole star detonates in a runaway thermonuclear reaction. Boom, supernova. Gone in seconds. That's a Type 1a supernova. It doesn't leave behind a neutron star or black hole, just scattered elements and shockwaves. But it's incredibly useful to scientists because these explosions always happen at roughly the same brightness. That makes them perfect cosmic measuring sticks. We use Type 1a supernovae to figure out how far away galaxies are and even to measure how fast the universe is expanding. So, to recap, massive stars collapse and explode. Small, dense stars can steal matter and blow up too. Different paths, same epic result, a supernova. And here's the thing, even though they're rare, we've been lucky enough to catch a few in action. One of the most famous ones in recent history is SN 1987A. It exploded in the Large Magellanic Cloud, a nearby galaxy, and it was so bright you could see it with the naked eye, even though it was 170,000 light-years away. That explosion taught us a ton about how supernovae work, especially what happens in the first seconds after the blast. But we've known about supernovae long before modern science. Ancient astronomers saw them too. In 1054, Chinese astronomers recorded a guest star that appeared in the sky and stayed bright for weeks. That explosion created what we now call the Crab Nebula, a swirling cloud of gas and debris that's still expanding almost 1,000 years later. At its center is a tiny neutron star spinning 30 times a second, sending out pulses of radio waves and light, a dead star's beating heart, still ticking away. These explosions aren't just part of history, they're part of everything. The calcium in your teeth, the iron in your blood, the gold in your jewelry, the silicon in your phone. All of it came from supernovae. We owe our very existence to stars that died long before Earth was even formed. And yet, for all we've learned, there's still so much we don't fully understand. Like, what really triggers a collapse at the exact moment it happens? How exactly does the shockwave form and escape? Why do some stars turn into black holes while others don't? The deeper we look, the more questions we find. But there's one thing we know for sure. These explosions aren't just violent ends. They're part of a much bigger story. A cosmic recycling program. The universe takes and the universe gives back. What dies in one place becomes the seed for life in another. So what happens after the blast? What's left behind? Let's keep going. So the star explodes. It's gone. But it doesn't just disappear without a trace. What's left behind is often even stranger than the explosion itself. Depending on the size of the original star, the aftermath can take one of two very different paths. If the star was big, but not too big, its core gets crushed into something incredibly dense, a neutron star. And I mean dense. Imagine stuffing the mass of the entire sun into something only about the size of a city. Just 1 teaspoon of neutron star material would weigh about 1 billion tons. It's like matter stripped down to its most extreme form. Protons and electrons get squeezed together into neutrons. That's it. Just pure neutron matter, packed tighter than anything else in the universe, outside of black holes. Now, if the star was even bigger, truly massive, it doesn't stop at a neutron star. Gravity just keeps going, unstoppable, until it forms a black hole. This is where things get weird. Really weird. A black hole is a point in space with gravity so strong, not even light can escape it. Time itself slows down near the edge, and anything that falls in, it's gone, at least as far as we know. So either way, neutron star or black hole, the core becomes something unrecognizably alien. But the rest of the star, that gets thrown into space, forming what's called a supernova remnant. It's a huge, expanding cloud of gas and dust, glowing with heat and light, and often shaped by the blast wave's chaotic energy. These remnants can last for thousands of years, lighting up the sky with filaments, swirls, and shockwaves that stretch across light years. And here's the beautiful part. Those clouds don't just drift around aimlessly. Over time, they can start to come together again, pulled by gravity, compressed by waves from other explosions. Eventually, they form new stars, new solar systems, new planets. In other words, a supernova doesn't just destroy, it creates. It sends raw materials back into the galaxy. where they can be reused in future generations of stars. And if the conditions are just right, somewhere in that mix, maybe life appears. So in a very real way, we are children of supernovae. Everything we are, everything we see, comes from those violent deaths. The air we breathe, the ground we walk on, the thoughts we think, they all exist because some star exploded billions of years ago, and its ashes drifted through space until they became part of us. It's humbling. It's wild. And it changes how you look at the sky. Suddenly, those tiny pinpricks of light become something more. They're not just stars, they're stories, each one burning its own path toward a future explosion, a future transformation, a future beginning. But that raises another question. These explosions are out there, happening in other galaxies all the time. But what if one happened close by? Could a supernova ever affect us here on Earth? Let's talk about that next. So, what if a star exploded near us? It's a fair question. These things are powerful, so powerful they can outshine an entire galaxy. So what would happen if a supernova went off close to Earth? Could it wipe us out? Would we even see it coming? Let's break it down. First off, space is huge. Most stars are incredibly far away, and even when a supernova happens in our galaxy, it's almost always at a safe distance. But there are a few stars close enough that if they went supernova, we'd notice in a big way. The most talked about candidate is Betelgeuse. You've probably seen it. It's that reddish star in the constellation Orion, one of the brightest in our sky. Betelgeuse is a massive star, hundreds of times larger than our sun. It's old, unstable, and showing signs that it's nearing the end of its life. At some point, tomorrow, or maybe 100,000 years from now, it's going to explode. And when it does, wow. From Earth, it'll be brighter than the full moon, visible even during the day. Not dangerous, but unforgettable. People will walk outside at night and see a second sun hanging in the sky. Cultures across the world will look up in awe, confusion, maybe fear, and scientists will be absolutely thrilled. But here's the important thing. It won't hurt us. Betelgeuse is about 640 light years away. That's close in cosmic terms, but still far enough that when it goes supernova, the radiation and shockwave will have fizzled out by the time it reaches us. We'll get a light show, not a catastrophe. Now, if a supernova happened really close, like within 30 light years, it'd be a different story. The high-energy radiation, especially gamma rays, could seriously mess with Earth's atmosphere. It might strip away parts of the ozone layer, exposing the surface to more UV radiation from the sun. That could hurt plant life, disrupt ecosystems, and cause chain reactions through the food web. Not instant doom, but not great either. Some scientists even think this might have happened before. There's evidence, like certain isotopes in deep-sea sediments, that suggests a nearby supernova might have occurred about 2 to 3 million years ago, possibly influencing climate shifts or even extinction events. Nothing definitive, but it's on the table. Luckily, we don't know of any stars close enough right now to pose that kind of risk. Betelgeuse, Antares, Rigel, those are all too far away to harm us. So while supernovae are something to respect, they're not something to fear day to day. If anything, they're reminders of how connected we are to the universe and how lucky we are to witness it from a safe distance. And that leads to something even more fascinating, because as terrifying as a supernova might sound, its legacy is one of creation. These explosions are the engines of cosmic evolution. Without them, the universe would be a very dull place. Imagine a universe with only hydrogen and helium, the two simplest elements. That's what the early universe looked like after the Big Bang. No carbon, no oxygen, no iron, no gold. Just gas. It was the first stars, the giants, that began fusing hydrogen into heavier elements, and it was their deaths, their supernovae, that scattered those elements across the cosmos. That's how galaxies formed. That's how planets formed. That's how chemistry became biology. Every time a star explodes, it enriches the galaxy with material that can become part of something new. You don't just get stardust floating around for fun. That stuff gathers, it forms clouds. Those clouds collapse and form new stars, and often planets around them. And maybe on one of those planets, life sparks into existence. So you see, we're not just looking at explosions. We're looking at the heartbeat of the universe. The rhythm of death and rebirth over and over again. The ashes of one star become the building blocks for 100 new worlds. And you're part of that, literally. The iron in your blood, the calcium in your bones, the oxygen in your lungs, all of it was forged in the core of a star that exploded long before Earth even existed. That's not poetry. That's astrophysics. The story of the supernova isn't just about stars dying. It's about everything that comes after. The beauty and destruction, the possibility born from chaos, the way the universe recycles its matter, building something new out of what was lost. And there's still more to explore. Because when we look at the remains of these explosions, the supernova remnants, we see incredible structures, glowing clouds stretching across space, neutron stars spinning like cosmic lighthouses, even black holes hiding in the darkness, bending time and space, and each one tells us something. Each one holds clues about how the universe works and where we come from. Let's go there next. After a supernova, the star itself is gone, but it leaves behind something remarkable, something that in many cases we can still see thousands of years later. These are supernova remnants. Imagine a giant glowing cloud of gas and dust, spreading outward through space at millions of kilometers per hour. It's the remains of a star, still radiating with the energy of its final breath. The shapes are complex, swirling filaments, shockwave ripples, tangled webs of glowing atoms. Some of them span dozens of light years across. One of the most famous examples is the Crab Nebula, the remnant of a supernova seen by Chinese astronomers in the year 101054. What they saw looked like a new star suddenly appearing in the sky. It was bright enough to be seen in daylight for weeks. What's left behind today is a stunning cloud of colorful gas, orange, blue, violet, still expanding outward almost 1,000 years later. And in the center, a neutron star, spinning incredibly fast, about 30 times per second, sending out beams of light and radiation like a cosmic lighthouse. We call it a pulsar. It's the dead core of the star, still alive in a way, still moving, still telling its story through signals that travel across the universe. These remnants aren't just beautiful, they're important. They push and shape the space around them. The shockwaves from a supernova can trigger nearby clouds of gas to collapse, creating the next generation of stars. It's like a cosmic chain reaction. One death leads to many births. One explosion echoes through the galaxy, stirring the ingredients for something new. And sometimes inside these remnants, we find the most mysterious objects in the universe: black holes. A black hole forms when a collapsing star is so massive that nothing can stop gravity from pulling it into a single point, a singularity. Around it, space warps. Time slows. Light itself bends and gets trapped. We can't see a black hole directly, but we can see its effects. How it pulls on nearby stars, how it heats up surrounding gas, how it distorts light from behind it. What's incredible is that supernovae are one of the main ways black holes are born. These objects that break our understanding of physics, they come from the death of stars. They're part of the same story. Same beginning, very different end. But we don't need to go that far into extremes to see how supernovae matter. Even without creating black holes, these explosions change the chemistry of the universe. The elements they scatter become part of everything. Think about this. When our solar system formed, about 4.6 billion years ago, it wasn't made from pristine material. It was made from recycled stardust. At least one, and maybe more, nearby supernovae had already gone off. Their explosions mixed heavy elements into the cloud that eventually became the sun, Earth, and all the planets. The gold in your jewelry, that probably came from one of those ancient blasts. The uranium in nuclear reactors, supernova. The iodine in your thyroid, same. You're carrying the aftermath of stars in your body right now. It's not metaphorical, it's literal. And now we can study these remnants in incredible detail. Telescopes like Hubble, Chandra, and now the James Webb Space Telescope are giving us sharper, clearer images than ever before. We can see the structure of gas clouds, trace the fingerprints of different elements, and even watch how these remnants evolve over time. We're not just looking at pretty pictures, we're doing archaeology on a galactic scale. Each remnant is a clue, a puzzle piece, a snapshot of how matter behaves under the most extreme conditions, how atoms form and break apart, how the universe cools and changes, how time moves on after destruction. But there's still one more layer to all of this, because for all the science, all the physics and math and data, there's something deeply emotional about supernovae. They're reminders of something we feel in our own lives all the time. The idea that even the biggest, brightest things can come to an end, that change is constant, that destruction isn't always the end of the story. In fact, sometimes it's the beginning of a much bigger one. The universe doesn't waste anything. Every death feeds into a new life. Every supernova in its own way writes the next chapter. And when you step back far enough, you can see the pattern. The same atoms that once fueled a distant star now fuel your thoughts, your heartbeat, your breath. So when we talk about supernovae, we're not just talking about distant objects in space. We're talking about ourselves. We're talking about where we came from. We're talking about what it means to be made of stardust. Not just in a poetic sense, but in a real, physical, measurable way. And there's one last question we should ask. Where do we go from here? How do these explosions fit into the even bigger picture? The life and death of galaxies, the expansion of the universe, the fate of everything. That's where we're headed next. When you really start to zoom out, when you stop looking at individual stars and start thinking about galaxies and the universe itself, you realize something amazing. Supernovae aren't just part of the picture, they shape the picture. They're not just events that happen randomly in space, they're drivers of change, cosmic architects. Every galaxy we see, spiral, elliptical, irregular, has been sculpted by countless supernovae over billions of years. Think about a galaxy like the Milky Way. It's made of stars, yes, but also huge clouds of gas and dust, the raw materials for building new stars. Without some kind of energy to stir things up, to compress that gas, nothing would happen. Stars wouldn't form. Everything would just sit still. But supernovae shake things up, literally. When a star explodes, the shockwave races outward at thousands of kilometers per second. It crashes into surrounding gas clouds, compressing them and triggering new bursts of star formation. This is called positive feedback, a cycle where death leads to new birth. One generation of stars makes the next possible. But there's also negative feedback. If too many supernovae go off at once, they can actually blow gas out of a galaxy entirely, especially smaller ones. This shuts down star formation for a while. In that sense, supernovae act like galactic regulators, turning the dial up or down on how fast a galaxy can grow and evolve. And the energy they release? It's staggering. One supernova can release more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. Multiply that by millions of explosions across a galaxy's history, and you start to see how powerful these events are on a cosmic scale. Even more incredible, we now know that supernovae helped shape the universe itself. Remember those type 1A supernovae? The ones that come from white dwarfs stealing matter and exploding in a flash of carbon fusion? Because they all explode at nearly the same brightness, we can use them as standard candles to measure distances in space. In the late 1990s, astronomers used them to study how fast distant galaxies were moving away from us. What they found was shocking. Instead of slowing down like everyone expected, the expansion of the universe was speeding up. Something was pushing everything apart faster and faster. That discovery changed everything. It led to the idea of dark energy, a mysterious force that makes up about 70% of the universe, but that we still don't fully understand. And we wouldn't have discovered it without supernovae. These explosions gave us the data we needed to realize that the universe isn't just coasting, it's accelerating. So in a weird way, supernovae helped us find out that most of the universe is made of something we can't even see. Talk about irony. But this is what supernovae do. They reveal things. They don't just light up the sky, they light up our understanding. Every explosion is a message written in light and heat and motion, telling us something new about how the cosmos works. And here's another way to think about it. If you lived in a galaxy without supernovae, somehow, if that were possible, it would be a dead place. No new stars, no heavy elements, no planets, no life, no you, no me. Supernovae are loud and violent and chaotic, but they're also essential. They're the universe's way of shaking things up, of making sure nothing stays static for too long. They're part of the reason there's variety and change and complexity in the cosmos at all. And maybe that's why we're drawn to them, not just as scientists, but as humans, because in a way, their story mirrors ours. Something burns bright, it struggles, it runs out, and then, if it's lucky, it leaves something behind. something beautiful, something powerful, something that might help spark the next thing. The universe is full of cycles like that: birth, life, death, transformation. It's the same rhythm over and over again, from stars to galaxies to us. So, where does it all go? What happens to the universe in the long run after all the supernovae have burned out, after all the stars have lived and died? That's the final chapter, and we're getting closer. So, what happens when the explosions stop? Supernovae are loud and bright and unforgettable, but they're not eternal. One day, not soon, but eventually, the universe will run out of fuel for them. The stars that can explode will all have exploded. The galaxies will grow quieter, and we'll be left wondering what comes next. Let's fast forward. Not thousands of years, not millions. Let's talk billions, even trillions of years into the future. Right now, the universe is still young. It's about 13.8 billion years old, give or take. But stars are still forming. Galaxies are still busy. Supernovae are still going off. We're living in the golden age of star life, the period when the cosmos is most active, most alive. But star formation won't last forever. Eventually, the gas and dust needed to make new stars will run out. Supernovae, while they recycle and stir things up, also blow a lot of that gas away, especially in smaller galaxies. Over time, galaxies lose more material than they gain. The fuel supply drops. The factory slows down. First, the biggest stars disappear. They burn hot, live fast, and die young, most in just a few million years. Then, over billions of years, the medium-sized stars fade. And finally, the red dwarfs, the smallest, dimmest stars, will be the last to go. Some of them will burn for trillions of years, quietly, patiently, until they, too, flicker out. When the last star dies, the universe will go dark. There won't be any more light, at least not like we know it. No more warm suns, no more new beginnings, just the cold remnants of what used to be. White dwarfs cooling into black dwarfs, neutron stars spinning in silence, black holes drifting like ghosts. Some scientists call this future the degenerate era, a time when the universe is made mostly of leftover corpses of stars. No more fusion, no more supernovae, just the long, slow fading of heat and motion. But even then, strange things might still happen. For example, it's possible, in a far, far future, that some of those old black dwarfs could explode in rare thermonuclear events, something like a final whisper of the supernova age. It's theoretical, but if it happens, it could be one of the last fireworks in the entire cosmos. And then, entropy wins. The second law of thermodynamics tells us that over time, energy spreads out. Heat evens out. Systems become more disordered. The universe moves toward a state where everything is the same temperature. No hot, no cold. No structure, no contrast, just a vast, quiet darkness. That's the heat death of the universe, the ultimate endgame where time still exists but nothing happens anymore. It's not an explosion, it's a whisper, a slow dimming into forever. It's strange to think that something as wild and explosive as a supernova is part of a timeline that ends in total silence. But maybe that's what makes them even more valuable. They're fleeting, temporary, bursts of meaning in a universe that's always moving forward. And here's where we bring it all back. Because even though the universe has this long, quiet fate ahead of it, we're not there yet. We're here in the middle of it all, alive during a time when stars still shine and explode and create, a time when we can look up at the sky and see light that traveled for millions of years just to reach us. And that, honestly, is a gift. We get to be conscious in a universe that creates supernovae, that sculpts gold from fire, that throws the ingredients for life across the void, that turns death into possibility over and over again. We're made of the universe, and we're able to look back at it, ask questions, make meaning. That's extraordinary. It means the universe doesn't just create matter, it creates curiosity. And that curiosity, that hunger to understand, is what makes the story of supernovae more than just science. It makes it human. Because we've always looked up at the stars, trying to figure out what they are, what they mean, what they say about us. And now we know they don't just light the night, they made us. And someday, long after we're gone, long after Earth itself has cooled, the atoms that make us up will still be out there, drifting, waiting, maybe becoming something else. Maybe part of a new star. Maybe part of a new story. We've talked a lot about what supernovae are, how they explode, what they leave behind, how they shape the universe. But how do we even know all this? We can't exactly fly out to a supernova and take a look up close. These things happen light years away in distant galaxies, and the explosions themselves are over in seconds. So, how do we study something so far away, so unpredictable, and so short lived? Well, the answer is we watch, and we wait, and we build better and better tools. Astronomy today isn't just about looking through a telescope anymore. It's about gathering light, not just visible light, but every kind of signal the universe can throw at us. Radio waves, X-rays, gamma rays, neutrinos, gravitational waves. Each one tells a different part of the story. When a supernova happens, it doesn't just give off light. It sends a flood of radiation across the spectrum. And that's where modern telescopes come in, each one tuned to a different frequency, each one catching a different piece of the blast. Take the Hubble Space Telescope, for example. And it's been orbiting Earth since 1990, and it's helped us see the details of supernova remnants with more clarity than ever before. The expanding tendrils of gas, the layers of ejected material, the fading glow of the shockwave, all of that in full color from space. Then there's Chandra, the X-ray telescope. Supernovae give off tons of high-energy radiation, and Chandra helps us see the hottest parts, where gases are being heated to millions of degrees. This tells us about the energy of the explosion, how fast it's expanding, and how it's interacting with the space around it. More recently, the James Webb Space Telescope has joined the game. With its infrared vision, it can look through dust clouds and see things we've never been able to before, like the earliest stages of star formation triggered by ancient supernovae, or the chemical fingerprints left behind in the debris. And that's just the light. In 1987, when supernova 1987A exploded in a nearby galaxy, scientists detected something else: neutrinos. These are tiny, almost massless particles that barely interact with anything. They're produced in huge numbers during a core collapse supernova, and they escape before the light even gets out. That was the first time we'd ever detected neutrinos from outside our solar system. A huge deal. It gave us direct evidence of what was happening deep inside the dying star before the explosion even reached the surface. And now, with gravitational wave detectors like LIGO and Virgo, we're opening up another way to observe the universe. Someday, if two neutron stars merge, something that can happen after a supernova, we might not just see it and hear it, but feel it ripple through space-time. We call this multi-messenger astronomy. It's like switching from a black and white TV to full surround sound, color, and 3D. We're not just seeing explosions, we're experiencing them from every angle. And every time we catch one, we learn more. We learn how stars die, yes, but also how they lived, what they were made of, how long they burned, what kind of galaxy they were in, whether they had companions, whether they left behind something strange. And we're getting faster. Now, thanks to powerful computers and AI, we can sift through massive amounts of sky survey data in real time. We can spot the early signs of a supernova and point all our instruments toward it within minutes or even seconds. The goal? Catch one in the act, from the very first spark to the final fading glow. Because the truth is, for all we know about supernovae, we've still never fully seen one unfold in real-time detail. Every new observation gets us closer. Every new explosion is a chance to sharpen our theories, test our models, and find out what we got wrong. Science isn't about certainty, it's about chasing the unknown. And supernovae? They're the ultimate unknown. Unrepeatable, uncontrollable, massive, mysterious. They challenge everything we think we know about physics, about time, energy, even gravity itself. And that's exactly why we keep watching, because maybe the next one will teach us something new. Maybe the next one will change the story all over again. Long before we had telescopes or satellites, people were already watching the stars. They didn't know what supernovae were, not in the scientific sense, but they saw them. They noticed when something bright and strange appeared in the sky, something that hadn't been there before. And when it happened, they paid attention, because when a supernova goes off close enough to Earth, it's impossible to miss. It outshines entire galaxies. It appears where no star had been, blazing like a second sun. It can be visible even during the day, casting shadows at night, hanging in the sky for weeks or months. For ancient people, this was no small thing. It was a message, a sign. Something from the gods, maybe, something that demanded to be seen. One of the earliest documented supernovae happened in the year 1054. Chinese astronomers wrote down that a guest star appeared in the sky, brighter than anything they'd ever seen. It was visible in daylight for 23 days and glowed at night for almost 2 years. They marked its location in the sky with incredible precision. Today, we know that explosion as the Crab Nebula, the remains of a massive star that went supernova nearly 1,000 years ago. And when we look at it now with telescopes, we can still see the swirling gas and the neutron star left behind, spinning dozens of times per second like a cosmic lighthouse. But the Chinese weren't the only ones who saw it. In the American Southwest, the ancestral Puebloans carved a drawing into the wall of a cliff, a starburst next to a crescent moon. Based on the moon's phase and the position of the carving, some researchers believe it's a record of the same supernova. That carving has survived a millennium, a permanent memory etched in stone. It's kind of amazing to think about. People, separated by oceans and culture, all witnessing the same cosmic event. No science, no telescopes, just their eyes in the sky. There were others too. In 1572, the Danish astronomer Tycho Brahe saw a brilliant star appear where none had been before. He called it a new star, a nova stella, and his meticulous observations helped prove that the heavens weren't fixed and unchanging, as people had believed for centuries. This was a turning point. It meant the sky could change, stars could die. In 1604, Johannes Kepler saw another. He studied it with the best instruments of the day, still just basic lenses and careful note-taking, and wrote detailed records that we still read today. We now call that one Kepler's supernova. But after that, things got quiet, at least in our galaxy. It's been more than 400 years since the last supernova visible to the naked eye from Earth. That might seem strange, but remember, the Milky Way is vast and space is full of dust. Most supernovae happen too far away or too obscured for us to see with our own eyes. Still, we've never stopped looking, because the night sky isn't just a backdrop. It's a story we've been reading for thousands of years. And every once in a while, a new chapter appears. Bright, sudden, unforgettable. And maybe that's what makes supernovae so special. Not just what they are, but what they mean. They remind us that the universe is active, alive, in motion. That nothing, not even the stars, lasts forever. And at the same time, they connect us to everyone who came before. All the humans who looked up, saw something new in the sky, and tried to make sense of it. Whether they were scientists or shamans, monks or farmers, they all felt the same awe, the same pull, the same feeling that something enormous and mysterious had just happened above them. We feel that too. Even now, with all our technology, all our knowledge, all our models and simulations, we're still looking up and wondering. And when the next supernova happens close enough for us to see, the world will stop, just for a moment, and remember what it's like to witness something truly cosmic. Not just as scientists, but as people. When people hear the word supernova, they usually picture one kind of event, a massive star blowing itself apart in a huge fiery death. But in reality, there isn't just one kind of supernova. There are different types, caused by different kinds of stars under different conditions. And the more we look, the more variety we find. Let's start with the two big categories, Type 1 and Type 2. It sounds technical, and it kind of is, but the names actually come from something simple, how the explosion looks when we capture its light. If a supernova spectrum shows hydrogen, it's Type 2. If it doesn't, it's Type 1. That's it. That's how the classification started. But those labels led us to realize there are deeper differences. Differences in what kind of star exploded, how the explosion happened, and what it left behind. Type 2 supernovae are the classic kind, the death of a massive star. These are stars that live fast and die young. They run out of fuel, their core collapses, and then boom, the outer layers explode outward. We've already talked about this kind a lot. They leave behind neutron stars or black holes. They blow off clouds of gas that enrich the galaxy. They're messy, violent, and beautiful. But then there's Type Ia, and these are something else entirely. A Type Ia supernova doesn't come from a massive star. It comes from a white dwarf, a small, dense stellar remnant, usually the leftover core of a star that was never massive enough to explode on its own. These white dwarfs are stable unless something pushes them over the edge. And that something usually involves a companion star. In a close binary system, a white dwarf can slowly steal matter from its partner, siphoning off gas like a cosmic thief. If it takes in too much, it reaches a critical mass, about 1.4 times the mass of the Sun, and suddenly everything goes nuclear. The entire star detonates in a thermonuclear explosion. No core collapse, no neutron star left behind, just total obliteration. What makes Type 1a supernovae especially important is that they're incredibly consistent in brightness. They all explode at roughly the same energy, so they act like cosmic standard candles. We can measure how bright they appear from Earth, compare that to how bright they should be, and figure out how far away they are. That's how we discovered that the universe is expanding faster over time, by using Type 1a supernovae to measure distances across deep space. In a very real way, these exploding stars helped reveal the presence of dark energy, one of the biggest mysteries in modern physics. But wait, it gets weirder. There are some supernovae that don't fit into neat boxes, like Type 2n supernovae, where the N stands for narrow. These are explosions that happen when a massive star has already shed huge amounts of gas before it explodes. When the supernova shockwave slams into all that dense material, it lights up in a completely different way, producing narrow emission lines in the spectrum. It's like the star set its own trap and then fell into it. And then there are the superluminous supernovae, the biggest, brightest explosions we've ever seen. These are 10 to 100 times more luminous than a typical supernova, and we still don't fully understand them. Some might be powered by exotic processes like magnetars, rapidly spinning neutron stars with intense magnetic fields. Others might involve stars so massive they undergo something called a pair instability collapse, where the very nature of matter and energy goes sideways and leads to a full annihilation. Rare, enormous, mysterious. There are even failed supernovae, cases where a star's core collapses directly into a black hole without any visible explosion at all. The star just disappears. And if we weren't watching, we might never even know it happened. And every time we think we've seen it all, something new shows up. Astronomers have spotted supernovae that flicker on and off, like they're trying to explode multiple times. Others that happen in environments that should be impossible. Some that involve stars that were already weird to begin with, like those rich in helium, or surrounded by disks of material, or located way outside the normal boundaries of a galaxy. It's a reminder that we're still learning, that space is full of surprises, that the more we look, the more the universe shows us how little we truly know. But that's what makes supernovae so compelling. They're not just explosions, they're puzzles. And with every strange spectrum or unexpected light curve, we get a little bit closer to solving them. Or maybe not solving, maybe just understanding. Because sometimes the point isn't to figure it all out, sometimes it's just to look up and be amazed. It's easy to think of supernovae as things that happen out there, distant, spectacular, but not really connected to everyday life here on Earth. But the truth is we've felt their effects, not just in the distant past when the elements in our bodies were first forged, but maybe even more recently. Some scientists believe supernovae have left their fingerprints right here on our own planet. Let's start with the most ancient connection, chemistry. The iron in your blood, the calcium in your bones, the iodine in your thyroid, those didn't come from Earth. They didn't even come from the sun. They were born in stars, massive ones, and released when those stars exploded. Billions of years ago, long before Earth existed, those elements were scattered into space by supernovae. They floated through the galaxy, mixed with clouds of dust and gas, and eventually became part of the solar system that formed our planet. So when we say you're made of stardust, it's not a metaphor. It's literal. Your body contains atoms that were created in supernova explosions. But there's more. Sometimes supernova don't just shape what we're made of. They might actually influence what happens to us, and in some cases, what happens to all life on Earth. There's evidence that supernova may have triggered mass extinction events, not directly, not by blowing up close enough to fry the planet, but through a kind of chain reaction. Here's how it works. When a star explodes within a few hundred light years of Earth, it can shower our planet with cosmic rays, high-energy particles that blast through space at near-light speed. Normally, Earth's magnetic field and atmosphere protect us from most of them, but a nearby supernova could spike that radiation dramatically. That increase might not kill life instantly, but it could damage DNA, trigger mutations, or weaken ecosystems. It could also change the chemistry of the atmosphere, breaking apart molecules like ozone and letting more ultraviolet light through from the sun. There's some intriguing data to support this idea. In 1999, scientists found deposits of iron-60, a radioactive isotope that doesn't naturally occur on Earth in deep-sea sediments. It had to come from a nearby supernova. And the timing? About 2 to 3 million years ago. Not long ago, geologically speaking. Around the same time, Earth went through a minor extinction event and some major climate shifts. Coincidence? Maybe. But it's enough to make you wonder, and it's not the only case. More iron-60 has been found in lunar soil, left behind from cosmic fallout that hit the moon just as it did Earth. These little radioactive breadcrumbs are clues, pointing back to stars that exploded relatively nearby in what's now called the local bubble, a region of space carved out by multiple supernovae over the past 10 million years. So we're not just floating safely in space, we're moving through the wreckage of ancient explosions, shock waves, radiation, and awe. But here's the fascinating part. It's not all bad. While some supernovae may have contributed to extinctions, others may have actually helped spark life. One theory suggests that radiation from a nearby supernova could create lightning storms on a young Earth, which in turn might have triggered the formation of complex organic molecules, the very building blocks of life. In other words, the same cosmic forces that might have wiped out some species may have helped others begin, or evolve, or thrive in new environments. It's a strange kind of balance, a cosmic push and pull, destruction and creation, risk and reward. And through it all, Earth just keeps spinning. Life finds a way to adapt, to change, to survive. Sometimes when we talk about space, it feels like a different world, something separate from us. But the more we learn about supernovae, the more we realize they're part of the same story. The story of stars, the story of life, the story of us. They shaped our chemistry. They may have shaped our biology, and who knows, they might shape our future, too. When you think about the universe, it's tempting to picture it as something calm and majestic, vast stretches of space, distant galaxies floating in silence. But really, the cosmos is more like a storm, constantly in motion, chaotic, full of energy and change. And at the heart of that storm, supernovae. These explosions might happen to individual stars, but their effects ripple out across entire galaxies. They're not just dramatic events, they're essential ones. Without supernova, galaxies wouldn't look or act the way they do. In fact, the universe itself would be a very different place. Let's start with one of the most important roles supernovae play. They recycle matter. When a massive star explodes, it blows its outer layers into space and with heavy elements forged in the final stages of its life. That gas spreads out into the galaxy, where it mixes with other material. Eventually, that same gas can cool, collapse, and form new stars, and those stars can form planets around them. Without supernovae, there wouldn't be enough of the heavier elements to build rocky worlds like Earth. There wouldn't be enough oxygen or carbon or nitrogen for life. You wouldn't have gold or silver or copper. Stars would form, burn hydrogen, and die quietly, but nothing else would really happen. Supernovae kick off that next chapter. They seed the galaxy with fuel for future generations of stars and planets. In that sense, galaxies are like massive recycling systems, and supernovae are the engines driving them. But it's not just about matter, it's also about energy. Supernova pump huge amounts of energy into their surroundings. When they explode, they send out shock waves that can compress gas clouds and trigger the formation of new stars. But sometimes the opposite happens. The explosion is so powerful that it blows apart a gas cloud before it can collapse, halting star formation instead. This push and pull has a massive impact on how galaxies evolve. In a way, supernovae act like a kind of cosmic thermostat, regulating when and where stars are allowed to form. Without that control, some galaxies might burn through all their fuel too quickly. Others might never get started. So if you've ever looked at a spiral galaxy and thought, that's beautiful, you have supernovae to thank for that balance, that structure. They help sculpt those arms, distribute elements, and control the rhythm of creation. And this doesn't just happen in quiet corners of the cosmos. In the early universe, back when everything was hotter, denser, and more chaotic, supernovae were going off constantly. The first generations of stars were enormous, unstable, and short-lived. Their explosions helped spread the first heavy elements into space, kicking off a chain of events that eventually led to galaxies, solar systems, and life. They lit up the darkness. They transformed the void into a place full of possibility. Even now, some of the most powerful telescopes, like the James Webb Space Telescope, are pointed at distant galaxies looking for the light of ancient supernovae. Because that light carries information about how the universe looked billions of years ago. It's like cosmic archaeology, digging through layers of time, one explosion at a time. And when we study those early supernovae, we're not just learning about dead stars, we're learning about how everything began. But what about the future? Well, supernova will continue doing what they've always done for billions of years to come. Stars will live and die, gas will be recycled, and galaxies will keep evolving. But there's a limit. Eventually, star formation will slow down. The universe will run out of easy fuel. Things will get colder, quieter. This is sometimes called the heat death of the universe, a time when everything's spread too thin and there's not enough energy left to do anything interesting. But we're nowhere near that yet. Right now, the universe is still busy, still messy, still alive with fire and fusion, and the occasional brilliant, violent burst of a dying star. And even when things start to quiet down, the fingerprints of supernovae will remain, etched into the structure of galaxies, the chemistry of planets, the bones of living things. Because if you zoom out far enough, you start to see that supernovae aren't just events. They're part of the architecture of the cosmos. They shape the story, from the first sparks of light to the last flickers in the dark. For all their power, supernovae are incredibly hard to catch in real time. Think about it. A star can live for millions, sometimes billions of years, and then in its final moments, it explodes over the course of just seconds. That brief flash of energy travels through space for maybe hundreds or thousands of years before it ever reaches us. By the time the light arrives, the star has already been gone for ages. So how do we spot something that's that fast, that rare, and that far away? We watch. Constantly. Across the world and far beyond it, astronomers have set up networks of telescopes scanning the skies, every night, all night, looking for sudden changes, bright spots that weren't there before, or things that were faint and suddenly flare to life. One of the biggest tools in this hunt is a system called automated sky surveys. Telescopes like Pan-STARRS in Hawaii or the Zwicky Transient Facility in California take images of the sky over and over again, comparing them to past data to spot anything new. If something's changed, if a star has brightened dramatically, alerts go out to astronomers all over the world. And that kicks off a kind of scientific relay race. Teams scramble to point other telescopes at the event, in visible light, in infrared, in X-rays, even in radio waves. Each kind of light tells a different part of the story. The goal is to gather as much information as possible before the explosion fades. Because that's the thing. A supernova doesn't stay bright forever. Some fade within days, others in weeks or months. But once they're gone, they're gone. We only get one shot at watching them unfold. That's why space telescopes are so important. Take the Hubble Space Telescope, for example. It's captured some of the most detailed images of supernova remnants ever seen, like the famous Crab Nebula, which is the aftermath of a supernova recorded by Chinese astronomers in 1054. Then there's the Chandra X-ray Observatory, which looks at the high-energy side of these explosions, the incredibly hot gas and shock waves rippling through space. Or the James Webb Space Telescope, which can see the faint infrared glow from the dust and molecules created in these stellar deaths, helping us understand how galaxies build themselves from the inside out. But we're not just watching from a distance. We're also listening for neutrinos. These tiny, almost massless particles fly straight out of a collapsing star's core before the light even escapes. They travel through space, through planets, through people, almost completely undisturbed. But deep underground, in massive detectors filled with pure water or heavy chemicals, a few of those neutrinos can be caught. And when that happens, they tell us that something big has just happened, maybe a supernova, even before we see it. In 1987, for example, a star exploded in a nearby galaxy called the Large Magellanic Cloud. Astronomers saw it as a bright point in the sky, SuperNova 1987A, but neutrino detectors caught the signal a few hours earlier. That moment changed everything. It confirmed key predictions about how supernovae work. It proved that these invisible messengers could give us a kind of early warning system. So now, if another nearby star explodes, scientists hope to detect the neutrino burst before the light even arrives. That way, we can swing our telescopes into action, catch the moment from the very beginning. But what if it wasn't just nearby in cosmic terms? What if a star exploded within our galaxy, maybe even close to Earth? The good news is the odds of that happening dangerously close are tiny. The nearest massive stars capable of going supernova are still dozens or hundreds of light years away, far enough that we wouldn't be in danger from the explosion itself, but we'd see it. Oh, we'd definitely see it. There are a few famous candidates, like Betelgeuse, the bright red star in Orion. It's about 650 light years away, and it's nearing the end of its life. When it goes, it'll be spectacular, not dangerous, but bright enough to be visible even in daylight, a new star shining in the sky for weeks or even months. Another is Eta Carinae, a monstrous, unstable star system about 7,500 light years away. It's already had a massive eruption in the 1800s, and when it finally explodes, it could be one of the brightest events we ever witness with the naked eye. If either of these stars were to go supernova in our lifetime, it would be one of the most extraordinary celestial events ever seen. A cosmic fireworks show, live. And thanks to modern technology, it wouldn't just be a light in the sky. We'd catch it in X-rays, gamma rays, neutrinos, gravitational waves across the entire electromagnetic spectrum. Data would pour in from satellites, ground-based observatories, even radio antennas. The world's scientists would be united for that moment, racing to study one of the rarest and most powerful phenomena the universe has to offer. And we'd all get to watch, not just as observers of space, but as participants in something ancient and cosmic and awe-inspiring. Because even though supernovae are rare, even though they're far away, they remind us that we're part of the same story, the same universe, the same explosion, just carried forward in time. Long before we understood what a supernova was, long before telescopes or satellites or physics, people were still watching the skies, looking up, wondering. And when a star suddenly appeared out of nowhere, bright, blazing, unfamiliar, it must have felt like a message, a warning, a miracle, or maybe something to fear. Because supernovae happen close enough, don't go unnoticed. In 1006 AD, a brilliant light lit up the night sky, so bright it was visible even during the day. Across the world, people recorded it. In China, Egypt, Europe. It was the brightest supernova in recorded history, and for months, it dominated the heavens. In 1054, another appeared. This one also made the sky glow for weeks. Chinese astronomers documented it in detail. Native American cultures carved it into rock. Today, we can still see what's left of it, a tangled, glowing cloud called the Crab Nebula. A reminder of a moment when people all over the world looked up and saw something completely beyond their understanding. These were more than just lights. They were omens, signs, symbols. In many ancient cultures, sudden appearances in the night sky, new stars, were tied to major events. The birth or death of a king, a coming war, the will of the gods. After all, if the heavens changed, surely that meant something here on Earth had changed too. That sense of awe never really left us. Even now, with science explaining what's happening, supernovae still inspire us. They appear in books and movies, paintings and poetry. They're used as metaphors for endings, for rebirth, for sudden revelation. A supernova isn't just a stellar event. It's a symbol, a story. In literature, writers use it to capture a moment of explosive emotion or irreversible change, a relationship falling apart, a revolution beginning, a final act of beauty and destruction all at once. In science fiction, supernovae are both threat and wonder. They power starships, they end worlds, they birth new ones. They're written into the fabric of imaginary galaxies, treated with the reverence they deserve, as forces of nature so vast that even futuristic civilizations struggle to contain or comprehend them. In music, the word itself, supernova, has a kind of rhythm to it. You'll find it in lyrics, in album titles, in songs about love and collapse and everything in between, because it captures something raw, the idea that beauty can be brief but unforgettable. And in visual art, from paintings to digital renders, the imagery of a supernova is endlessly inspiring. Swirls of color, explosions of light, chaos and symmetry all at once. It's like trying to paint the soul of a star. Even the way we speak reflects this fascination. We say people explode onto the scene. We call someone a rising star or describe a once-in-a-lifetime talent as a supernova, something or someone that burned brilliantly, even if only for a moment. It's strange, isn't it? How a distant astronomical event, something that happens millions of light years away, can feel so personal, so human. Maybe it's because supernovae are, at their core, about transformation. A star dies, but in dying, it creates, it spreads the elements of life, it triggers change, it becomes something new. And that's a theme we recognize in ourselves, in our stories, in our lives. The idea that even in destruction, there's purpose, that endings can lead to beginnings, that light can come from loss. So when we look up at the sky and imagine those stars going supernova, we're not just thinking about space, we're thinking about us, about what it means to shine, to burn out, to leave something behind, to be part of something bigger. It's not just science, it's not just myth, it's memory, it's meaning. By now you've heard the science. You know what happens when a massive star runs out of fuel, the collapse, the explosion, the shock waves, the light traveling across the void. You've heard how it spreads elements into space, recycles matter, creates the conditions for life. But let's pause here just for a moment, step back, zoom out. Because the more we understand about supernovae, the more they seem to speak to something bigger, something deeper than just physics or astronomy. They become a kind of lens, a way of seeing the universe, not just as a collection of things, but as a story with chapters, cycles, patterns. Stars are born, they shine, they die, but their death isn't an ending, it's just a turning point. Their atoms go on, their energy echoes forward, their light travels uninterrupted long after they're gone. And that's not just poetic, it's literal. The light from a supernova might take thousands or even millions of years to reach us. So when you look up and see that bright flare in the sky, you're seeing the past. You're seeing a moment frozen in time, the final breath of a star that may no longer exist, a message that traveled across the dark, untouched, just to reach your eyes. That's one of the strangest, most beautiful truths in all of science. We are always looking at the past. And the past is still speaking. The dust and elements from those ancient supernovae, the oxygen you breathe, the iron in your blood, the calcium in your bones, they're all remnants of explosions that happened long before humans ever walked the earth. We don't just live in a universe where supernovae happen, we live because they happened. Every person, every plant, every rock and ocean and breath, it's all stitched together from the ashes of stars. And in some small, mind-bending way that connects us to everything. When we talk about the universe, it can feel impossibly big, cold, empty. But when we follow the trail of a supernova, from birth to death to rebirth, we see something else entirely. We see continuity, we see meaning, because we're not separate from the stars. We're made of them, literally. And maybe that's why these massive explosions feel so personal, even though they happen light years away. It's not just light we're seeing. It's a kind of mirror, a reminder that we're part of the cosmos, that our own lives, with all their joy and heartbreak and uncertainty, follow a rhythm not so different from the stars. We're born, we change, we shine, we fade. And yet, just like a supernova, what we leave behind can go on, can shape others, can light the path forward. Maybe that's the real magic of a supernova. Not just that it's beautiful, not just that it's powerful, but that it teaches us something deeply human. That in our brightest, most transformative moments, even in endings, there's potential, there's creation, there's legacy. Supernovae remind us that even the most violent end can give birth to something new. A star dies, a planet forms, a life begins, a mind wanders, a voice speaks, and the story continues.